The history of species composition data analysis is one of a history of changes in predominant measures, predominant statistical approaches over time. If you remember what polar ordination is, you definitely qualify as an old timer. For the last 35 years or so, the dominant approach has been based on this, what I call a distance or dissimilarity-based approach, where the starting point is a pairwise measure of dissimilarity between two plots, assembled into a matrix that then provides the foundation for visualization or inference. Starting about 10 years ago, David Wharton and friends have argued for an alternative model-based approach where there's an explicit model for the data, and that model then provides the foundation for inference, and recently then the possibility of visualizing data by fitting continuous latent variables. Now, some people think that this is an either or, but in fact, in practice, you find people using both approaches in the same paper. So there are numerous examples in the last couple of years of folks using model-based approaches, many GLM and the MV-abund package in R, analysis for inference, and then a distance-based analysis to visualize the sample pattern in the data. What you find is if somebody has counts, they will frequently use a negative binomial distribution for the model-based analysis, and then pick a dissimilarity measure. And there's no consistency. Some folks have used Bray-Curtis, some folks have used a Euclidean distance. And to me, that bothers me. And that's because dissimilarity measures make assumptions about the data, as again, David Wharton has shown, especially about the variance to mean relationship. And what bothers me is that the dissimilarity measures that people are using for visualization make different assumptions than have been used in the model-based analysis. So there's a mismatch. I would prefer that an analysis using two different approaches at least uses the same assumptions for both sets of data. There are two ways you could proceed to do this. One could start with a dissimilarity measure and then try to figure out what the right probabilistic distance or distribution is to use in a model-based analysis. Or you can start with a model-based analysis and figure out what the matching dissimilarity is. I've been following the second approach for some time now. Previously, I've talked about dissimilarities for count data. Today, I want to derive and illustrate the uses of dissimilarities for continuous data. So the basic idea is something I call model-based dissimilarity. If we start with data for two sites, vectors I of species abundance, vectors of species abundance at sites I and J, and consider two models for those data. One where we have the same species abundance, so that each of the vectors follows some sort of distribution with a vector of mean parameters mu, which is the same mean parameter for both vectors. Additionally, there will be, or could be, nuisance parameters, for example, the phi, the overdispersion parameter in a negative binomial, and I'll talk about other nuisance parameters in a few minutes. So we have one model where we have the same species abundance. We have a second model where we have different abundances in the two sites. The deviance between those models, the difference in the log likelihood, or twice the difference in the log likelihood, is a dissimilarity measure. It's non-negative, it's symmetric, and the dissimilarity is zero only if the two species composition vectors are identical. They are commonly dissimilarities, not distances, because they may fail the triangle inequality. The idea is not new. It was proposed by Cook and Weisberg in the 1970s and called likelihood distance in a very, very different context. The details of the dissimilarity depend very much on the presumed distribution. Very simple case, if we assume that the data are normally distributed with a constant variance, the dissimilarity, the model-based dissimilarity, is the squared Euclidean distance. If we relax the assumption of a constant variance, we end up with a weighted squared Euclidean distance, a familiar measure, at least in some areas of species composition analysis. The problem, of course, is that species composition is rarely normal. And a very convenient family of distributions for continuous species composition data is the Tweedy family, which has 3 parameters. It has a mean, 1 parameter mu that controls the mean, 2 parameters that control the variance to mean relationship, so that the variance of y is the mean raised to a power psi multiplied by a scalar phi. This family is a superfamily of distributions, including the normal, Poisson, and the gamma. And the most intriguing collection of distributions for species abundance data are those where the power, psi, ranges between 1 and 2. In that range, the Tweedy is the sum of a Poisson number of gamma distributions. That random number of distributions could be 0, which generates a point mass at y equals 0, which is a very common attribute of species composition data, and a positively skewed distribution for positive abundances. If you haven't seen the density function for a Tweedy, here's one example. As I say, a point mass at 0, and then a skewed distribution of non-zero values. So what we need to do is to figure out, for that distribution, the log likelihood under a model where we have different species compositions summed over the 2 vectors, and subtract from that the log likelihood, again for those 2 vectors, under the common model. There are 2 issues in doing this for a Tweedy. We have to evaluate the log likelihood first, and it's complicated for a Tweedy because there's no closed form expression. One can numerically evaluate the density. The d-Tweedy function applies a couple of different ways of approximating it depending on where in the parameter space you are working. But there's an alternative, which is the extended quasi-likelihood approximation from Nelder and Pregobon. That approximates the higher order moments, the lower order moments of that distribution, and you can write the contribution to the deviance, or half the deviance, in closed form as a function of the various parameters. So when the power is in between 1 and 2, this is exceedingly fast to calculate, and in every data set, it's essentially the same as the exact computation. To illustrate this, here is a comparison of the exact numerically evaluated dissimilarity for a variety of sites, and the one for the extended quasi-likelihood. The other thing you have to do is to compute the maximum likelihood estimate under each model using extended quasi-likelihood. That's very straightforward, and the MLEs are obvious in a sense and can be numerically evaluated very, very quickly. I'm going to skip the second point in the interest of time and move on to some examples. An example, this is data from the Park-Grass experiment, which, if you don't know about it, is worth knowing about it because it is the longest running, continuously monitored ecological experiment in the world. Started in 1856 and continuously monitored since. What we have are different fertilization regimes running in here and vertical bands across the plot, different liming regimes in horizontal bands. And in total, there were 4 lime levels. There are 14 fertilizer treatments. I'm going to consider just 2 lime levels and reduce the fertilizer effects to just a nitrogen level, using data from species composition in a couple of years, where we have hay biomass by species and plot. If you fit a Tweedy distribution using the many-any function, using a model where we have additive nitrogen effects and lime effects, we find strong evidence for effects of nitrogen and effects of lime. If we use the default diagnostics from many-any, which are diagnostics at the observation level, which are very good for evaluating the variance to mean relationship, we see that that plot looks reasonably good. Model-based dissimilarities provide sample-level diagnostics and sample-level plots rather than observation-level diagnostics. So we can take the estimated phi and psi parameters from the many-any analyses, use those with the observed species composition to calculate dissimilarity, apply non-metric multidimensional scaling, and we get a plot like this, where each one of these points is one of the samples. They are color-coded by the lime level, and the numbers are the nitrogen level. We see here that there is indeed a trend from no nitrogen plots with one sort of species composition to another set with higher nitrogen levels. We can evaluate, and this is done without any model. So this is a model-free diagnostic. We can evaluate whether in fact the linear effect of nitrogen is reasonable because each of these dots represents one sample. There's a nitrogen level associated with each sample. We can then smooth those nitrogen levels. And here you see contours of nitrogen levels from a thin plate spline, and they sure look reasonably linearly spaced across the ordination space. We can calculate from the many-any model predicted species composition, and one can overlay that predicted species composition into the multidimensional space. That's very easy to do with metric multidimensional scaling. It's a computational challenge for non-metric multidimensional scaling, but one can just simply do non-metric multidimensional scaling on an augmented vector, augmented data set, adding the predicted species composition. Doing that, you notice that the projections of predictions can be quite different from the default usual dissimilarity-based measure of sort of an average group composition, which is the centroids. So here I'm contrasting the location of the centroid for a group to the projected prediction of species composition. And that's because of the nonlinearity associated with projection into the non-metric space. We also have residuals at the sample level, which are dissimilarities between the observation and the prediction. And one can plot those in a variety of different ways to gain understanding about perhaps plots that are or are better or less well fit by the particular model that we're using in the many-any. I focused on abundances. One can alternatively look at species proportions, either by conditioning on the sample total and using that as an offset, or using a zero inflated beta distribution and the same ideas. I've worked out all the details. I'm not going to talk about them here. And an alternative, you may be thinking, is model-based ordination, which we'll hear about later today. That's a latent variable model where we use the latent scores as an ordination plot. It does show patterns between the sites, but no longer are distances on paper related to dissimilarity between the samples. And that's because of the identifiability concern, where each component of the latent vector is normed to 1. Practically, this can be very slow to fit, and you'll hear about, I believe, faster ways of fitting this. I gave up after 60 minutes trying to fit the Tweedy model to this very small parkgrass data set. There are a couple of lingering issues specifically for the Tweedy distribution that deal with which model are we going to use to estimate those nuisance parameters, connections between the probability of a 0 and the moments of the non-zero distribution, which are issues with Tweedy distributions in particular, which zero inflated beta distributions do not have those issues. And I'll be happy to talk about those later for anybody that is interested. So what I've hopefully motivated is the value of a traditional like dissimilarity measure based on the same assumptions that have been made in a model-based analysis as a tool to visualize multivariate species composition in a fast way, making essentially the same assumptions about the data, as a tool for overlaying predicted multivariate composition at the sample level onto a plot of sample composition data points, and as a tool for constructing sample level residuals. The details in all cases depend on the choice of distribution. And I'm happy to talk more about this later, either through Slack or there's my email address, and I will be very happy to answer questions. Thank you very much.